Can you hear me okay? I've got I've got some new headphones, new earphones, like fake AirPods things. Um, yeah, they seem to work quite well, but they drop out if I don't speak loud enough. What in the world is that? That's what I'm about to explain. If I could get a confirmation on the audio, and then yeah, cool. Okay, so this is now the third stream, I think. I wanted to do some 3D printer stuff. I had some modifications to make to this, which is the first 3D printer I bought. Bought it around 3 or 4 years ago, um, and I've already modified it quite a bit, but there's some more things that I want to do to it right now. So I'm just going to talk through some of those and then do some work on it as well. So the printer is a Wanhao i3 Plus. So it looks like this. And you can see it has, I'll bring this closer here. Um, so this is the print head. This is where the plastic kind of comes through, gets extruded. And then it has three axes, right? So there's this bed that moves back and forth. That's the y-axis. This entire gantry, which the print head is suspended on, moves up and down. That's the z-axis. And then the x-axis is the movement left and right. So if I show you on the actual printer, the x-axis here, so the last one I spoke about, is that. The bed sits on top of this plate. It's not this plate, but it sits on top of a plate like this. Get it lined up. Sits on top like that and moves back and forth. That's your y-axis, and then your z-axis is obviously this, moving up and down. In terms of the modifications I've done already, you can see these braces for strengthening, which are attached down here. And there are some other things which you can't see, but that I will be dealing with. So 3D printers actually, for something that's so magical, quite a simple device. Let me grab some filament and I'll show you kind of how this works. It's quite linear and quite easy to understand. So let me just find some filament here. Okay, I can't find any spare filament. I had some bits lying around, but so when you print with a 3D printer, you use some of this stuff. It's called filament. It's basically just a roll, a spool of plastic, right? Solid plastic, but flexible. What the printer does is it extrudes that filament, right? It moves around and extrudes that filament. That's basically its two kind of jobs in terms of movement. So if I zoom in, show you a close-up view, you still hopefully have the big view in the zoomed out view in the bottom right, but this is the hot end. This is what does the actual printing bit, right? So the axes that we talked about for movement, they decide where you print. This decides how the printer actually gets plastic into the shape that you want. So this hole here, the filament goes in through that hole and it gets pulled through by this motor here. So if we look at this kind of right to left, it's quite a simple stack of things, right? Quite linear. So we have a motor which draws the filament through this. So this is called the extruder. So this has a gear that grabs onto the filament and rotates, thereby pulling it through. Would this be considered the typical 3D printer? In terms of home 3D printers, yes, this is the typical kind of printer that you would buy as a kind of first 3D printer, or in terms of consumer 3D printers, this is the style that you would usually buy. It's called an i3 style, and it has this characteristic of there being the bed for the y-axis, bed movement here, and then a z-axis that moves up and down like this, that moves a gantry, and then an x-axis that's suspended on that gantry. That's the typical kind of 3D printer. So motor, extruder, which is run off the motor. Then we have here a heatsink and a fan, right? So this is these are for cooling. Um, and what they do is they cool the hot end, right? So we've kind of described this going this way. And in order to describe what a hot end is, I need to describe the downwards direction. I don't really have a view of that now. But the thing that I need to do right now is actually to remove this and modify it. So what I'll do is I'll take this off and then flip it around, and we'll be able to see how the filament actually travels through this and actually gets into a solidified piece of printed material on the bottom. So there's just some two screws here underneath this assembly here, which I'm just going to try and remove. I'm not sure what size they are exactly, but I'll start with 2mm hex key. I think that should be right. Yeah, not really coming out. So the issue with this Z-axis is you can see down here actually, there's some screw threads. So all of the other axes you can kind of move by hand quite easily. The Z-axis you can't because it's quite kind of highly geared because of this worm gear setup. So I can't just lift this up to get a tool underneath, unfortunately, which is quite annoying. What I might do actually is plug it in and raise this gantry up so that I get better access underneath. So let me just do that quickly. Before I do that, just to prevent this getting tangled, you see this moves back and forth on the belt here. And I've taken the belt out because I want to retension it. So I'm just going to take it out fully as well, just so it doesn't get in the way. So there's another screw there that I need to get that out. Because I was touching these screws. I've got some grease on my fingers, so I can't hold the Allen key properly. Okay, so if I take this out now, there's probably easier ways of doing this, but okay, probably easier way. It's out from that side, isn't it? Let's look through. I don't know why, but I always end up doing really fiddly things on stream. Okay, so that's the belt out. And the reason I want to change it, or not change it, but the reason why I want to retension it is because it has this tensioning mechanism here, just a little spring. And it's basically not very good. It allows a lot of slop into that movement, and that results in some artifacts on your prints that you don't want. Okay, so that's out. Now I'm just going to grab a cable, plug in the printer, and raise this up so that I can get a screwdriver underneath here. to make sure it's off before I plug it in. And it is. So just takes the kettle lead in the back. This is in a weird state of disassembly, so hopefully it doesn't. Hopefully, like, this all works. I don't think there's anything unplugged that's going to prevent this from working, but let's just see. Yeah, it's turning on. So unfortunately you can't see the screen here, but yeah, I'm not going to be able to get that in frame. It's got a touch screen on the front, and I'm just going to go into here, go into controls and move, I'm going to say Z up. I'm just going to hold that down, and you'll be able to see that the gantry is moving up. Here's the close-up view. You can see all of that's getting closer to the camera. That should be enough. What I'm going to do, I'm going to leave the printer turned on for now, because I want to move it back down later. But see if you can hear this actually. If I put my headset near the printer, I'm going to press a button here that says disable motors. Okay, that was silent anyway. So these motors, that's a good way to explain. Okay, so this is your y-axis movement motor, right? You can see I'm moving it back and forth right now, and there's no resistance. It just moves. When you have the printer kind of engaged and turned on, those motors are under control, even though they are still and steady. They're under control by the electronics. So usually, so if I were to say move Y, I now can't move that by hand, right? It's kind of locked in place. As soon as I hit disable motors, I can now move it. So the reason I disable the motors is just because I'm going to be fiddling around with it. And if you're pushing against a motor that's trying to stay still, then obviously that's going to cause some issues. So just disable the motors for safety. It doesn't matter here because obviously the belt is disconnected, and also I've unplugged the motors on the back of here, so there's no power getting to that anyway. Okay, so that was a 2mm screw. If there are any issues with audio quality or anything else, just let me know. Okay, so I need a 2mm screwdriver for this, and that is what that is. Okay, so this assembly is just held in with two screws. Once it's down, I'll be able to show you a bit more of what I've already done to the printer. So it's going to move the Z-axis back down, just to give you a better view of what I'm doing here. Okay, so there's a ribbon cable, big thick cable that comes onto this board here from the rest of the printer, which I've removed, which connects this entire assembly electrically to the rest of the printer. What I need to do now is, obviously, if I want to remove this, I've got to unplug everything that's connected to it. So that's the motor wire that I just unplugged. This is for the fan. There's a couple more things that I need to remove, which I'll explain in a second. There's one on the underside here as well. Okay, so now this should just come off. I need to remove this wire from this side as well, because it's kind of catching. Okay, I'm not going to reuse that cable. It's bad practice to pull cables by the cable bit. You should always pull on the connector itself in case the cable pulls out from the connector. But I'm not going to reuse this cable. And it's usually fine anyway. The force is kind of shared between all 4 pins, so it's usually not a problem. Okay, this will come out now, hopefully. Cool. That's out. What I'm going to do, yeah, okay, let's explain this a little bit more. So if I move this out of the way. So we went through what was happening here horizontally, right? So you've got a motor extruder. So the motor drives the extruder, pulls filament through this hole, and you've got a heatsink and a fan to cool that heatsink, right? So why do you have a heatsink here when this is essentially called a hot end assembly, right? So this is the hot part of the printer. Why do you want to get rid of heat? Well, there's a couple of reasons you want to get rid of heat down here. So if I look at it this way up, you can see again, motor, extruder, heatsink, fan. This is called a cooling block. Different printers will have different designs for doing the thing that I describe here. But what you see here is the hot end itself, right? So you've got the extruder, you've got a cooling block, then you've got what's called a heat break in between the cooling block and the heating block. And then you've got the nozzle. So this nozzle is where your printed filament comes out. And as you can see, it's already a bit messy from some filament that's kind of been printed and then been touched by this. It always ends up a bit messy, and I have, there are ways around that. You can wrap this in some silicone, and I have some molded silicone pieces, which are called socks, to go over this once I've cleaned it. But what happens here, if I show you from this side, you've got a heating element inside here, which is this little circular bit here, and you've got a temperature sensor, which is this bit here, right? So those are your electrical connections into your heating block. So your filament comes down through here, and it gets heated up at this point, right? And then pushed through the nozzle, pushed by the extruder up here. Because it's being pushed by the extruder here, you want your filament to be solid all the way down, right? Until you get to the heating block. Because if you have liquid here, you're not going to push it through, you're just going to make a mess, right? So that's why you have this very abrupt change between a hot part of the printer and a cold part of the printer. So this heatsink and fan call this cooling block. So the idea is that you want to maintain the coldness of the filament all the way through here, all the way until it reaches the heater, and then you want it to melt pretty quickly so that you can push it through the nozzle and print whatever you want to print. So you'll see that the heat break, let's see if we can bring that closer, you can see how the heat break is kind of, it's got a very narrow section there, right, which is the actual bit of the heat break that does the thermal breaking, right, the thermal barrier. And obviously there's a gradient in there, right? So you're transitioning from solid to liquid somewhere throughout this chamber, but you want that process to be as quick and as abrupt as possible so that you get consistent extrusion with a solid, and then obviously like consistent melting, right? To get your print, your melted filament out onto a print. And then once it's out, you want it to cool quickly as well. So most printers will have another cooling fan or a set of cooling fans which blow air directly onto the area just below the nozzle, so that when you're printing, your print cools immediately. And that means that when you're printing things with overhangs, you're not waiting for the gradual cooling of that, which would allow it to kind of droop while it's cooling, right? If it's still liquid, it's not going to stay rigid as it's printing. So you'd have another cooling fan blowing directly onto the nozzle or just below the nozzle, which will cool the filament as soon as it hits your desired location to print it and kind of solidify it in place there. Not kind of, exactly solidify it in place there. So this is like fairly simple. And this is what makes a 3D printer work, right? In terms of the physics of actually printing material, this is all of it. What I want to do here, I've already made some modifications. So this heating block and this heat break itself, sure I didn't show you that, this heat block and the heat break itself are upgrades. The cooling block's also an upgrade, but it's a minor upgrade. These heating elements are capable of much higher temperatures, but more importantly, this heat break is much more efficient, right? So this is called a bimetallic heat break. And it does that kind of abrupt change between solid and liquid a lot better than other kinds of heat break. So what I want to do, let me explain what the modifications we want to do right now are, because obviously I've worked on the efficiency of this, and now what I want is a bit more kind of print volume. I want a bit more area to be able to print. So if I kind of put this loosely back, that can work. ignore the fact that it's wonky for now. So I said you have your bed here. Okay, and on top of your bed, you would usually have a build surface. So I have this aluminium plate, which is heated. I'll go into why it's heated like a little bit later, but it's essentially for adhesion. I'll just say that. So the lower the differential in temperature between your filament hitting the first layer of your print and the actual bed temperature itself, the more likely it is to stick to the bed. So this bed has a heating element in it driven by these wires. And then there'd be a build surface on top of this. So I use glass usually, but I'm going to experiment with a new surface as well. And what I want to do here, this is 220 millimeters wide, 22 centimeters at its square. So in both directions, 220 millimeters. The build volume of my printer is 200, I think, 200 and something, maybe 210 or a bit. I think it's 200 millimeters. So essentially the nozzle right now doesn't go to the edge of the printing surface. And I could do with a bit more space. And so what I'm going to do is I'm going to use a smaller motor so that I can go further in this direction. And I'm going to change this end stop here. So all this is a switch. It's a micro switch. If I'm quiet for a minute and stop talking, you can hear it clicking, right? So all that happens is that when this moves far enough to the left, it hits on the frame of the printer and it triggers. So the printer knows that that's the 0 point on the x-axis, right? When that happens right now, there's a gap. There's a small gap. If I switch to the other camera view, here, you'll see that there's a gap here between the fan and the frame of the printer. So the Z-stop's triggered, but we actually have a little bit more space that we can play with in terms of print area. So what I want to do is, close up. What I want to do is to move this Z-stop this way so that we can take advantage of that space, and then use a smaller motor on this side so we can take advantage of the space on this side as well. So I have taken some measurements, and I'm really bad at these things, actually, measuring things, and like I'm sure I'll find an error in my calculations when I come to actually do it. But I've measured each element that I told you about here. So the motor, the extruder, the heatsink, and the fan. And the actual space that I've got to play with on the left right now, so the actual increase in print area that I could get, is about 14 millimeters. I have 4 millimeters on the left before it hits the end stop. I have 10 millimeters on the right. So if I get a motor that's 10 millimeters narrower than my current motor, I can essentially use the entire bed to print on. So that's what I did. I went and bought a narrower motor. Now, obviously, a smaller motor is not necessarily a better motor, right? Generally, in terms of motors, size equals power. So I'm compromising a bit of extrusion power with this, but I do have, where did I put the rest of that stuff? Get behind here. So I do have a motor that's quite a bit narrower, right? Now this was sold as a 23 millimeter narrow motor. Let's get them lined up. There we go. I actually measured it, and it's like 24 or 24.5, which means I'm not going to get the full range that I wanted on this side, unless, and this is a trick that I saw based on another manufacturer that's manufactured another hot end for this printer, unless I flip around part of the assembly. So if we look at this, you'll see that the cooling block's held in by these two screws, and they're symmetrical. If you flip the cooling block around, you actually end up, because you can see that this is offset to the side here, right? So the actual heat break doesn't go in the center. So if you flip this around, you end up with the heat break on the other side. And because this cooling block is where the entire assembly mounts to the printer, you end up shifting the entire assembly in this direction. So if I combine that shifting with the smaller motor, I can take full advantage of the entire width of the bed here. That's what I'm planning to do. And that requires some modifications here, because when you flip this around, you can see, obviously, it's not in the center that way as well. So I need to kind of drill a new hole here, make a new cutout for it to sit in, which I won't do on stream because it will be very noisy and messy, and wreck all, like, wreck anything, but it'll get dust onto my desk and stuff, which I don't want to do here, right? But what we can do is kind of work on this bit and reassemble this bit. And maybe, as we usually do, we'll encounter some problems along the way in terms of incompatibilities. These motors are a standard size. You'll see here it says NEMA 17. Let's see if I can get that. There you go. NEMA 17 stepper. So that refers to the size of the shaft, the location of this ring, and the size of these holes, etc. So it does follow some standards. These are both NEMA 17 motors. I should just be able to replace this, but we'll see if that's the case or not. Will flipping it affect the printing process or the quality? No, because everything stays in the same orientation relative to itself, right? We're just changing the kind of the way these things interface with the outside world and the rest of the printer, but in regards to each other, everything stays the same. Essentially, all we're doing is taking this heat block and rotating it 180 degrees, which is completely fine. So this is all held together with just 2 screws here. They go all the way through this assembly and screw into the motor. So by taking those out, this will all fall apart, and we can have a look at some of the mechanisms I described in closer detail, and we can get this new motor on. I do also have, while we're here, a new gear, but I'll come to that. I'll come to the gear section when we've taken it apart, and you can see what the gear is. So what I'm going to do right now, I'm just going to give myself a bit of a table to work on here. I'm going to grab some more. Yeah. Okay. So this is quite interesting as well. This is a sheet of FR4. This is what printed circuit boards are made of. And like I said, I used to print on glass. So on top of this whole stack up, there would be a sheet of glass. And glass is a really good surface to print on because it's perfectly flat. If you buy float glass, that's pretty much the flattest surface you can buy, as a normal consumer and not, a university laboratory or something. And adhesion's okay on glass. Sometimes you need to, I use hairspray sometimes to get a stickier surface for the print to stick to. But there was a YouTube video recently from someone who said that this stuff works really well as a print surface. So I bought a sheet of this. And what this is essentially fiberglass board in layers with an epoxy binder. So it's a composite material, and it's fairly heat resistant. I tried to get a more heat resistant version, but it's really expensive. But I'm going to cut this down to size and use this as a print surface and see how well it compares to the glass. For now, we'll just use it as a work surface. So if I grab this, and all I need to do is undo these two screws, and hopefully this whole thing should come apart. Okay, that's the wrong size. It's not that small, is it? Yeah, it is. Okay, that's a 2mm screw. Wa alaikum assalam to everyone who said salam in the stream, by the way. Sorry, I haven't been keeping up with the chat. Yeah, thanks, Saki. Seems like we've got quite a good turnout for this one. Hopefully it's interesting. Okay. Cool. So you see these spaces just fell out. So the heatsink has some cutouts for these spaces to fit in. And that just keeps everything kind of aligned nicely. So that's the heatsink off. You can see how long these screws are, right? Ridiculously long. And they just tension the whole kind of thing together. So take those out. Remove this if you can afford it as well. Give you a better view. Maybe while it's still on, I just move the Z-axis out of camera frame as well and get a better view. Cool. Set it off now. Don't need the printer on anymore. Okay, so you can see here the cooling block that I talked about, and you can see this kind of matte area. You can see also here some white stuff. So that's thermal paste. It's just a liquid that helps with thermal conductivity between the two surfaces. So essentially, these surfaces aren't perfectly flat, and even if they're perfectly flat, they're not. Even if they're perfectly flat, they're not. They're going to have imperfections, scratches, things like that. And so this just fills in those imperfections with something that's thermally conductive. It's the same stuff you use. It's literally the same stuff you use on a computer heatsink or anything like that. You see, this just came apart because it was all just held by those screws, and they're not there anymore. You can see there's a bit of solid filament, which is a good sign, right, in this gap here. So on the entrance to the heat break. So like I said, the aim is to keep the filament solid all the way through here, and it looks like this setup has done that, right? So there's a solid piece of filament just left over there. And so this is the moving bit, right? This is the extruder. And let me get some filament again, and I'll show you how it works. So essentially, you have your roll of filament that's kind of suspended somewhere near or on the printer, and it enters through this hole on the top here, okay? And this is spring loaded for you to be able to load your filament. And you can see there's like an idler bearing here and a gear. So essentially this spins, and as it spins, you can see it pulls the filament through, right? And that's how it extrudes filament through then the cold section and then the hot section of the extruder. So like I said, very simple. The issue you have here a lot of the time is slippage. So on my other printer, I've replaced the extruder with what's called a dual drive extruder. So you have two gears instead of just a pulley for it to push against and one gear. You have two tooth gears. You can see here there's some teeth on those gears to allow it to grip the filament. So I've got that on both sides. We're quite space constrained here, especially with the kind of stack up thing that I want to do. So I don't have that here. What I can do though is replace this gear with a sharper one. So that's what I've done. I bought this gear here, which seems to be made of brass, so it's not steel like the one that I've got on there, but it is quite a bit sharper. You can see those are kind of almost, if it'll focus, it focused for a second there, didn't it? These are kind of almost razor sharp gears. It's not gonna play ball, is it? Okay. Hopefully you get a better view of that a bit later. So unload that filament. Okay, so we have another screw here which is holding the kind of extruder assembly onto the motor. So let's just undo that. Again, it should be the same size. It should be a 2mm. That screw that's either a Torx or a hex, but it's been kind of chewed up. So let's see if the screwdriver does any better with it. Yeah. Hopefully I've got a replacement screw. That doesn't look like one that I want to use again. Okay. I should give you a better view of this, shouldn't I? You can actually replace some of these parts with metal replacements. They're a bit expensive right now, so I haven't done that. So you can see here, this is a thing that pushes against the other side of the gear. It's got a groove in it to kind of allow the filament to sit there. And you can see it's quite loose as well. Maybe I do want to replace this sooner rather than later. But you can see it's kind of blackened with the amount of filament that's kind of been grinding against that gear when it hasn't been moving properly. Side note, this is a magnetic tray, but these screws in particular are not like they're not being attracted to it, that's because they're stainless steel. If you want to check here for fastener or anything really that looks like steel is magnetic, is stainless, just use a magnet. If it doesn't stick, stainless steel. So we've got the spring out of there, which is not stainless. That will, there you go, you see, that kind of wants to stay put in there. Okay, we've got one more screw here, quite a tight one. There we go. That's the old motor. So you can see this gear here is held on just by these two. These are called grub screws or set screws. That's how that gear is retained. But you can see also, if you look down here, you can see it's got a fully hollow circular shaft, but the actual drive part of the motor has a shaft, right? Has a flap in the shaft, so it's called a D shaft, right? Because it's shaped like the letter D. That's going to be important because the new gear, as you can see here, has a D shaft, right? Like I said, everything's a standard. This D should be the same across all motors, so this gear should fit straight onto our new motor, but we'll see if it does or not. And also, just checking if the kind of teeth on this are directional. They don't seem to be, right? If they're kind of angled like that, symmetrically, or if they're angled one way to kind of pull the filament in a certain way. They seem to be symmetrical, so essentially it means it doesn't matter whether we put our new gear on this way around or this way around. Again, we'll see. We'll see as we reassemble it. I'm just going to get a toothbrush and clean out all the debris from here, and then we'll look at our new motor. I would use compressed air, but I've run out of it. And when you get to the bottom of a compressed air can, you get the propellant gas coming out, which is really bad for you. Like I sprayed with some of that stuff a while back, and it just put me to sleep for a whole afternoon. I have no idea what it is, but it's definitely not safe. Okay, should be fairly clean. That's clean enough. Okay, new motor. So, in theory, let's just check which way up this was. So I'm guessing that was the bottom because it's got these marks from the heat break. And I'm wondering if I want to mount it another way up actually, because you remember we had some issues kind of finessing it off because of the way this connector was colliding. So I'm wondering if I want to mount it differently. Is that still in view? Yeah. Okay. I'm wondering if it would go this way up. If I were to put this, so it's going to be that way around now. So, okay, it does need to sit on top of here. But the wire could come out the bottom, which would be quite nice, or it could come out of the front, or it could come out of the side. Or the top. The top might be easiest, actually. Let's say it's going to exit from the top. So this is the bottom of the extruder. I need to clean off this thermal paste because we're going to flip this. Sorry. I need to clean off this thermal paste because we're going to flip this around. So the thermal paste will now be on this side. So what do I want to do first? Let's screw this on first. Let's get the top section of the assembly on first, and then we'll look at the rest. So this all looks like it's fitting so far without any issues. So we've got this screw here. And then we've got another countersunk screw. I'm going to see if I have a replacement because that one's kind of chewed up. So I have a lot of M3 screws. just kind of collected with the various projects. They're one of the more common sizes that I use. I'm not sure I have anything that's going to do what I want here though. Do we need a countersunk screw there is the question. Check the lengths of those. They are the same. I'm going to try this screw. It might be that it doesn't give us enough clearance to do what we want. Let's see. Let's check I don't have anything else that's comparable. No. In fact, I'll be able to check if we have any interference issues probably by make some space. Sorry, I missed that comment. I'm really slow at keeping up with the chat. Need some of it, Chief. Some of what? What did I mention that's in need? Okay. So this goes on here like so. And yeah, we do need a countersunk screw, obviously, because the countersunk's on this side. Okay, I can't replace that, but what I am going to do is measure it so that I know what kind of screw I need to buy to replace that one. So let me do that quickly. So when you're measuring the screw, you don't measure including the head, you just measure the length of the screw itself, and that is a 16mm countersunk M3 screw. I'll just note that down. Okay, cool. Let's make sure this one's nice and tight. If I put this in for alignment and then tighten the other one, that's probably a good idea. Just slack it off, make sure everything's aligned, and then tighten it back up. Obviously don't want to go too tight because this is plastic and it will deform quite easily. The dangerous stuff that makes you sleep. Yeah, it wasn't a good sleep though. It was, yeah, it was horrible. It was really not nice. Okay, so before I tighten that all the way, I'm going to put the spring back in, which provides tension here. It's quite a stiff spring actually. I'm not sure how far we'll get today because hopefully we get to reassemble all of this because I've got to leave in about 20 minutes. It should be enough for us to get this back together, but maybe not much more than that. Okay, so if I tighten this down, obviously now this screw that we're putting in is really a bearing as well as a screw, so we've got to be a little bit careful that we don't over tighten it because there's no other bearing in there, right? It's just the screw into this piece of plastic, sits on that piece of plastic, so it needs some movement in there. Again, another reason why a metal replacement for these parts would be good. Okay, this is now the tricky bit because I should probably take the spring back out because I'm going to need it out to adjust this. So the tricky thing here now is, like I said, D shaft, D shaft. Now I've tried this before. I cheated a bit, and the tolerances are really tight, right? So I can get the gear on that far, but pushing it on any further, it's just kind of, it's giving me a lot of resistance, right? So what I'm going to do is I'm going to try and make this hole bigger, right? The way I'm going to do that is by heating it up. So I've got two options, right? I can heat this up, I could cool this down, I could do both. I don't want to cool this down because if I put this in the freezer, it's going to get condensation, and that's not good for electronics, obviously. But if I heat this up, hopefully this expands enough for me to be able to slide it onto here easily. So I'm going to take this spring back out because I'm then going to need access once I've done that to this grub screw here to then tighten it on. So I'm going to need to be able to get a screwdriver or something into this gap here. So let me do that quickly. What do I need for that? I need a pick to get that out. Pick like this. There we go. And the way I'm going to heat this up is just with a heat gun. Just try and heat it quite evenly. So this is my heat gun. Again, cordless little system, really good. Like I can just use the same battery for like a soldering iron, a heat gun, impact wrench, air compressor, like loads of stuff. Just uses the same battery, which is really, really convenient. And I have a bunch of attachments for the heat gun. And if I use this one, which is designed for heat shrink sleeving, just goes onto there. Hopefully I can just sit that in there and heat it up. I'm not going to do it on camera because there's like a computer and monitors and stuff here and I don't want heat getting near those. So I'm just going to do that off camera. I'm also going to wear some gloves so that when I pick this up and try and put it back on, see, I'm not touching it with my bare hands. In fact, I probably need a spanner or something to... I'll figure it out. I need some tools to be able to press this on. So give me a second, bear with me, and I'll do that, and then we'll see if we can get the gear on. Okay, just see if this is how loud this kind of shows up on the microphone. So I don't want to drown out your eardrums with heat gun noises. So I'll turn the volume down if that's going to be an issue. I think that's okay. Dropped it. Great. Okay, back. So I can show you quickly. I'm just kind of holding it down like that so you can see the gear resting in there, and hopefully it's getting quite evenly heated. I can feel the heat coming back off at me. Hopefully you can still hear me over the heat gun. It's not loud, that's good. This heat gun, most heat guns generally tend to get up to about 300 degrees. I'm not sure if that relates to the air that they push out or just how hot the heating element gets. But we do need to get quite a bit of heat into this to make it expand enough to do what we want. The other option is oil, right? Some kind of lubricant that we can place in the shaft. But the issue with oil is that this gear, just going to rotate it on the heat gun to make sure it gets evenly heated. This gear is actually, it looks like a sintered metal gear, so it wouldn't, basically it's porous, right? Oil would leak through um, onto the plastic, which you don't want. I'll explain a bit about sintering in a second once I've got this off. Okay, that should be enough. Let's see if this is any easier now. So line up the D. So I'm going to do this quite quickly before it cools down again. You can actually see some scratches that have been left by the initial attempt at this. It looks like it's not any easier now. I'm just kind of trying to apply some pressure. And it's really not going anywhere. I think this grub screw is loose, but I'll just make sure, I'll just double check. Just in case that's rubbing and causing it not to be able to go on. Just, yeah, that's really hot. Right, so but it's not wanting to push on. It's a good fit, but it's a friction fit, right? We need a way to press this on right now. No, I don't want to force it and damage the motor. So let's try taking it off again. Just levering it. Because if it cools down on there, then obviously it's going to be stuck, right? Which we don't want either. Bear in mind, this is brass, this gear, and everything I'm touching it with is steel, so it's going to leave marks. This has not gone well. I had two really successful streams, so this is not bad going. It's still hot, but the issue is now it's going to have transferred that heat into the shaft, so the shaft's going to have expanded. Maybe I'm better off waiting for it to cool down. These are not particularly heat resistant gloves, but I'm going to just try pulling it off with the gloves on. Yeah, okay, it's coming off. Okay. Not the most successful thing. So you can see here on the shaft, actually, you can see how it's kind of marred the surface. Yeah, it focused for once. So there are some kind of scratches on the surface, which doesn't really matter, and I'm kind of glad that this is a good fit. And I can feel, actually, when I touch this shaft, I can feel how hot it is. So it's definitely, heat might be the way to go, but it's not, the first attempt was not successful. I'm going to have a think about how I do that. While I'm waiting for that to cool down, I'll explain about sintering. So you can see this gear. Maybe it'll focus again. That would be nice. It's still really hot. Okay. So it's, okay, yeah, it's focused. So you can see this gear is kind of a rough surface texture. It's not, it's not perfectly smooth. And even here you can see, yes, it's been ground flat, but there's kind of, it looks porous, right? And that's because it probably is porous. So how gears like this are made, so obviously machining is expensive, right? If you take a solid rod of brass and you have to machine it to this kind of tolerance, especially when you've got a hole in there that's not circular, right? Because a circular hole you can drill and ream, but how do you make a D-shaped hole, right? That's a difficult problem. So gears like this are injection molded a lot of the time nowadays, right? In the same way that plastic is injection molded, they do a similar thing with metal. So instead of melting the metal and pushing it into a mold, what they do is they create a mold and then they take granules of metal. So in this case, brass. They fill the mold with the granules. They heat it up to such a temperature and under such pressure that the individual of metal kind of melt together, right? So they don't completely melt and flow into the mold, become a liquid, but the outer surface melts enough that they kind of weld themselves to each other. So you end up with something like this, which is, I assume this is made using that process. So you end up with something that's in, a very specific exact shape and doesn't need any uh, or doesn't need much further machining to get the tolerances that you want. Um, and is also and that's obviously like a much cheaper process. But the downside is you end up with a gear that's less dense, has less metal in it because there's some air between all those grains, um, and also is slightly porous, right? Porosity is a useful thing with brass when you're making bushings and things like that, and you want to fill them with oil. You want the oil to impregnate the brass. In a place like this, it's not ideal because you're going to get filament leaching out onto, so you're going to get oil leaching out onto the filament just before it gets melted, and that's going to burn up and vaporize, and it won't cause any issues, but it's just best not to have that right before your heat break. So I'm not sure if oil's the solution. I think I need some way to locally cool this shaft and locally heat this, get it on quickly. Obviously, I'm not going to be able to do that on this stream. The other option is just hammer it on. Brand new motor that I've just bought. I don't particularly want to do that. So I think I'm going to leave the stream there for now, unless there's any questions. I've got to get going in 5 minutes anyway. In fact, is it 5 minutes? Oh, I've got to get going in like 10 minutes, so I do have some time. So the other thing I was going to do on this stream is terminate this connection. Right, so this connector here is not of the same type as the one on my motor, which was this. So should I do that now? I'll do that. I was planning for this to be the last stream on this printer, but I think we'll have another stream on this one. So so I'll do that next stream as well. What I'm going to do right now is just clean up these surfaces. And while I'm doing that, I'll keep an eye on the chat if there's any questions or anything that you want me to answer. I think in terms of how far I can get with this right now, this is it, which is less than I wanted, but that's fine. So yeah, I'll keep an eye on the chat. If you have any questions, let me know. So what I'm using to clean it is just alcohol, isopropyl alcohol. So this is the same stuff you get from pharmacists. It's the same stuff that you desanitize wounds with. Works really well as a solvent for cleaning stuff like this. And thermal paste gets everywhere, so that's why I'm cleaning it right now. Also called rubbing alcohol, because you rub it on wounds. Okay, so that was the side that I took the heatsink off, so that's now going to be the side that touches the motor, right? So I'm just going to mark it as well, so I know. That's my marker. Okay, that's the motor side, and yeah, so I'm not sure whether I'll do a stream for the rest of this. All I need to do essentially is flip this around, reassemble it. I'll do the flip around thing when I do it. Yeah, flip this around, reassemble everything. I told you I didn't think about these, I wasn't able to always think these things through all the way. I can't simply flip this around because the hole in the extruder is on this side. So I have to keep the orientation. Alcohol also dissolves permanent marker, which is useful. So unless I figure out, maybe there's a 3D printable version of these parts that I can print out, which would allow me to modify them and flip them around. I would still like to do that because obviously the whole point of this is to get the full range of travel. I don't think I'll get it unless I flip this around. So I can either buy a replacement for this. I know they make ones that go in either direction, um, or 3D print something, or figure out some other way of doing what I want to do. What's the difference between this printer and your other ones? Okay, so this printer, like I said, is a i3 printer. It's got a so I have two printers, right? So this is the kind of standard style, the classic 3D printer. It has four motors, so two for the z-axis, which kind of move in unison to move these to move the gantry up and down. One for the x-axis, one for the y-axis. It's called a Cartesian printer, right? Because everything uses Cartesian coordinates, at least as an input. Um, it's called Cartesian because it has the three linear axes, right? 1, 2, and 3. My other printer is called a delta printer, and it's very clever in the way that it works. I can't show it right. Actually, let me get up a picture of it. I'll explain how it works a little bit. Bear with me a second. I'll just try and pull up a good picture of my other printer. Okay, so this is my other printer. You can see it's quite different, right? It doesn't have those three axes that run in different directions. All it's got is three vertical axes, right? And what it does is it essentially through the movement of those axes and the ball joints between all of the components here, um, it's able to move the print head um, to any location in X, Y, or Z just by using linear motion, right? I don't know the exact maths behind it, but it does all of that maths internally, right? It takes Cartesian coordinates in, so it takes G code, which is the language that 3D printers and other machinery understand. It takes in G code that says move to a certain position in X, Y, and Z, and E, which is the extruder. Um, but it then does some mathematics internally to say, okay, that is equivalent to moving these actuators to a vertical position. So you can see quite simply that at the moment it's at its topmost position, right? If I wanted to move it down to its bottommost position, I just move all three down equally, right? But if I move them at different lengths, and you can see that there's two on each side, so the motion's constrained so it can't tilt. So if I move just this one down, you can just intuitively say that, okay, it's going to move away from me, right? Away from the camera. If I move this one, it's going to move in this direction, this way. If I move this one, it's going to move in this direction, right? And so it does all of that math internally, and it allows you to build, like with quite a compact footprint. You can build because triangles are so kind of rigid structurally, right? You can have quite a tall Delta printer, and like you see, build quite a tall model. If you try and do this on an i3 style printer, like the one we were just working on, you need to worry quite a lot about the rigidity of the frame and things, and um, that's why I've had to make the frame more rigid with these, right? Because when you have lots of fast movements here, um, and this frame is flexing, that's going to result in a reduction in print quality. So both are capable of really good prints. Both have advantages and disadvantages. I just got a really, this was a good deal when I got it 3 or 4 years ago. The Delta printer was a good deal when I got it like a year ago, right? And the plan is to use them for slightly different things. So the hot end components that I've used here are really well suited to. The camera's backwards, so it's hard for me to decide what I'm doing. But these hot end components are really good for high temperatures. So I can put really high temperature filament on here, and flexible filament, so rubberized parts, which I can't do on the Delta printer because it's called a Bowden tube setup, right? So the filament flows through this tube here, this white tube, So the extruder is actually up here. Everything we talked about on the printer that we're working on, instead of being down on the print head, is up here, right? The heating and cooling bits are down here, but the actual extruder motor and the gear system, as you can see, it's very similar to what we're working on right now, is up here. So you have this length of tube that the filament has to travel through before it gets heated. And if you have a flexible filament, that means that you're obviously like compressing it in that tube, and it just doesn't work very well. So yeah, yeah, cool. I think that's enough for today. The last thing I'll do, actually, I will just leave you with, we go back to close-up camera. They're both capable of really good prints. So this is a print off of this printer. You can see the kind of almost mirror finish. The non, you know, the kind that there's no roughness to this, right? The surface texture that you see, the kind of blemishes, are due to hairspray, which I used for it to adhere. Um, this is a really nice print, right, done on this printer. This is actually a part for the front of the printer to angle the screen up and give you access to, there's an SD card slot inside which you don't have access to usually. So you can replace part of the front of the printer with this and get access to that. So that's on my list of things to do to this printer, but you can see, it prints really well. Both printers print really well. But yeah, I just wanted to get a bit more print area out of this one because the Delta has a circular build area. This obviously has a square one, and it'd be nice to have a little bit more space. There's quite a lot of the time when I was working with this printer, I have to orient things at a weird angle to get them to fit onto the build plate, and an extra 10 or 20 millimeters might not sound like much, but it really makes a big difference in terms of what you can print on the machine. Cool. So that's it. Thanks everyone for tuning in, or whatever you call it nowadays. And yeah, I'm not sure whether the next stream will be on this or on something else. I have some things to do on the Delta. I'm not sure when it will be. Obviously, this stream with like the two cameras and everything took a while to set up, and I'd like to streamline that process before I do something like this again. But we'll see. Yeah, thanks for being here, and I'll see you next time.